Okay, AP Physics, here's your walkthrough for velocity vectors on motion diagrams. This will be a quick video. It's pretty straightforward to write velocity vectors, but before we do that, let's review what we did with displacement vectors yesterday. Go ahead and draw the motion diagram for this ball rolling down a ramp. You can pause the video here and do that. If you draw this, let's define a couple things before you do that. Is this ball moving or not to start? Let's say it's not, so we're stopped here. And that should help you with your motion diagram. And let's end the motion diagram right before it comes off the ramp here. So our first one will just be a dot here. Concentrate that whole mass as one spot there. We label it 0. And then we might do 1. And then we need a bigger space. We're speeding up as we go down this ramp. 2. And then an even bigger space. And every dot gets farther away from the previous dot as we go down this ramp. And we're accelerating. We're going faster and faster. Okay, that's what we've done so far. Hopefully in your packet with the displacement vectors, you've then added a little arrow between these, between 0 and 1, and you just call this delta R0 with an arrow above it. We draw another arrow here. This is delta R2, or 1, excuse me, and keep doing all the way down between all of your dots, and you label all these. This would be delta R2 and so forth, and I won't label all of them. But you label all these down. Now remember, this is a displacement vector. A displacement vector is simply the distance between these two, that's the magnitude of this vector, and the direction of that vector. And to get that, we just take our displacement vector for 0, and we have to have a defined origin for that. I just want to repeat how this works. If I define my origin right here, maybe this is 0, 0. That means my first vector is going to be a line from here to here. And this would be the displacement vector R0. And then I draw another line from here to here. This would be my displacement vector R1. And if I subtract those two, final minus initial, R1 minus R0, I get this delta R. Now, if you draw this plot out again, you can do this for every single one of these dots, and you can get that displacement vector. If you choose an origin over here and define this as 0, 0, guess what? If you draw the arrow from here to here and here to here for 0, 1, 2, 3, 4, 5, 6, and you subtract them, you still get that same delta R there. And what that means is we don't really care where the origin is. When we're drawing a motion diagram, all we care about is what does it look like from point 1 to 2, 3 to 4, and so forth. And that's all you need to have for your motion diagrams for displacement. Okay, we're going to add velocity to this, and to do that, we need to talk about time. Delta is our change in time, t final minus t initial. If we start at 4 seconds and we ended at 2 seconds, then we had a change in time of 2 seconds. And if we add this to the distance that we've traveled, we get something called average speed. And average speed has no direction. This is a scalar quantity. Scalars have no direction. This would be something like 45 miles per hour. So maybe I travel 45 miles, and I do that in 1 hour. And 45 divided by 1 gives me my 45 miles per hour. Okay, this is an average speed. I could have been going faster than that or slower than that while I'm driving. Just like in our Wolfpack 500, you calculate an average speed. You might have been going faster or slower at one point in the race, but this is our average for that. To make that a velocity, we need to have a direction. And to add a direction, all we do is we take our displacement vector. Instead of a distance traveled, d, we're going to take our displacement vector, which is our delta r. That's what we just drew here. This guy right here, this has a magnitude and a direction. And so instead of just saying 45 miles, it might say 45 miles east or 45 miles north. And if we divide that by our time, we get an average velocity, which we're going to put the little vector notation on. And our textbook simplifies that a little bit. We even drop out the average. We don't have to keep writing AVG over and over again. When we start doing math, we'll look at that more in depth. But when you get a motion diagram, here's all you're doing for your velocity ones. Draw your dots just like we did, connect them just like we did, and now instead of labeling it as a delta R0 vector, we're going to take that delta R0 vector, divide by the scalar of time, my change in time, and we get a delta V vector. It's just average velocity. And all you want to think about here is the greater the distance between our dots, the greater the average velocity. For a motion diagram, we're just creating a model to represent motion so we can compare multiple objects or the path of an object over time. So if we can compare the hare and the tortoise, All we need to do is simply say, well, this has a lower velocity because the dots are closer together. And that's all we're representing when we say V0, V1, V2. And in a row here, we're showing that they're all equal to each other. So it has a constant velocity. And so does the hair. They're all the same distance between them. And so they have a constant average velocity. If you're a critical thinker, you might not like the fact that this is the same length as our delta r vector, because if time is not 1 second, if I divide those two, I'm going to get a different length for my v velocity vector. If that all makes sense to you and you don't like that, that's okay. Right now, we're just making a model that shows how this motion compares to other particles moving. And we'll deal with that when we do math. If none of that made sense to you right there, that's fine. Just stick with our model that we're talking about right here. So let's go back to our motion diagram for the ball rolling down the ramp. We're going to do the same thing. We can label our dots here, 0, 1, and this is what you'll do in your packet. These should be getting farther and farther apart because it's speeding up. And I'm going to make this a velocity motion diagram by drawing an arrow between the two. And the only thing I change is I label this V with the arrow above it. It's a vector. It has a direction and a magnitude, 0. And I'm going to do the same thing. My next one between 1 and 2 is going to be V1. Always start with V0. That's my initial velocity. And then I'm going to have V2 and so forth. I won't draw the rest, but you'd go all the way down your ramp here. That's all you're doing for your motion diagrams for velocities. Let's consider one other motion here. If I was in class, we'd be throwing balls around. I'd be asking you to walk around the room and things like that for motion diagrams. But we'll just look at this. Draw the motion diagram for a ball tossed straight up into the air and caught when it comes back down to your hand. We only want the motion diagram from the second it leaves your hand to the second it lands back into your hand. So see if you can pause the video and draw that motion diagram. It should look something like this. I'm going to start at the point that I leave the hand. So here's the bottom, leaving the hand. And at this point, I'm traveling quickly. I'm throwing it up into the air. And so this is our point 0. And then my first spacing is going to be rather large, something like this. This is point 1. And then my next spacing is going to be closer together. This is point 2. And then I'm going to get even closer together. And maybe I label my point 3 right here. That's it going up. And now you have a problem because it's going to come back down over my same dots. And we don't know this yet, but it actually will travel the same way down as it went up. And I'm going to split this diagram and draw another line over here. Even though this is on top of it, I'm going to make this clear that these are two different paths. It's overlapping the paths, but we have two different travels here with time. This is still point 3. We're at the top of our path of travel. And now we're starting to go back down. We've turned around at point 3. So this would be point 4. And now as we go back down, we're getting faster and faster as we come back towards your hand. So I start with a small gap, and now I'm getting a larger gap for 5. And now an even larger gap for 6. And this will be the moment right before it hits your hand. If we want this to be a velocity diagram, I just need to draw my arrows in here. And I would call this V0. And my next arrow, V1. And my next arrow, that's smaller, V2. And my velocity gets lower and lower as the ball goes up. That should make sense to you. The ball slows down. At the top, the ball actually does pause for a millisecond, where it has no velocity. It's stopped and it turns around. Anytime you turn around, you have to stop for a millisecond. And then it's going to come back down, and I'm going to have V3. And now my velocities are getting bigger. V4, it's going faster and faster as it approaches your hand. And V5. And this is what it should look like when you do your velocity vectors in your little packet, okay? I want to jump to your packet real quick. This is number 13 in your workbook. Our figure here, I want to point out one thing. It shows the positions of a moving object in 3 successive frames. We start here at the 0. Draw and label a velocity vector V0 for the motion from 0 to 1 and from 1 to 2. So you should do something like this. This is all you're doing. V0 and then V1. And the reason I want to point this out, this is an average velocity. Does the object, whatever this is, actually travel along this path? The answer is it could. Maybe it's like a pool ball and it hits a wall and bounces off at a different trajectory. But it could also travel in a different path. Maybe the trajectory, and you had a question like this in your packet, maybe the trajectory, the actual path that that ball travels or whatever it is, looks something like this. It goes out, it curves, and then it comes out something like this. It could look like anything. The point is this: when we're taking any points in the path of travel for an object, we're simplifying that path of travel. So if there's a big curve here, we're simplifying that with 2 points and just looking at the average between these two, which we're going to treat as a straight line. We will make this more complex as we add to it throughout the year to be able to model travel with curves and things like that, but we're going to stick in one dimension for this first unit. Okay, I believe that's it. Yep, that's it for our velocity discussion. Hopefully that helps you with that next section of your packet. Send me any questions in an email if you have any.